Welcome back to CVE167 Pre-Stressed Concrete Design. So we are now on Module 3, Stresses Calculation. So yung previous module, we have discussed what are the stresses present in a pre-stressed concrete, either completely axial, centroidal axial, or um, axial force at an eccentricity. So for this module, we'll solve or calculate stresses given a certain problem. Okay, so for this lesson, we'll be calculating stresses in a pre-stressed structural members. Now, pre-stressed structural members commonly are beams, but there are also slabs and other structural members. So by the end of this module, you should be able to calculate stresses in a pre-stressed structural member. Okay, so review. So for the case 1, which is centroidal axial pre-stress, there is a pre-stress stresses due to pre-stress and stress due to loading. So the resultant stress or the maximum stress is the negative P over A due to pre-stress and plus minus um, bending stress due to loading. So ito yung for the case na axial pre-stress yung problem. Okay. So next is pre-stress at an eccentricity. So yung P natin is at a distance E below neutral axis or above neutral axis. So depende sa problem. So we have due to pre-stress, we have compressive stress and bending stress, and another bending stress due to loading na omega or sa other distributed loads. So the maximum stress present sa for this beam at this situation is negative P over A, that is due to the P, and then plus minus PEC over moment of inertia of the section BD, and minus plus bending stress MC over I due to loading. So in the case of a rectangular beam, so we can directly substitute the properties of a rectangular beam, the area, the C, which is d over 2, and the inertia. So this will be the formula for the case of rectangular beam. Okay, so let's solve some sample problem. Okay, so situation 1, given the following data of a pre-stressed rectangular beam. So we have rectangular beam. So beam dimension BH or BD is 300 by 600. So loads are superimposed dead load 5 kN per meter, live load 15 kN per meter, and unit weight of concrete is 23 kN per cubic meter. So the problem is the beam is simply supported on a span of 12 meters and are pre-tensioned with total initial force of 1,750 kilonewton from low relaxation strands with centroid 220 millimeter below the neutral axis throughout the beam length. So there is a 15% loss of pre-stress at service loads. Okay, so questions are calculate the stresses at the bottom fibers of the beam at the end span due to initial pre-stress. So bottom and top fiber, and calculate the stresses at the top fiber and also bottom fiber in megapascal of the beam at mid-span due to the service loads and pre-stressing force with a loss of 15% at service loads. Okay. And last is calculate the maximum additional uniform load in kilonewton per meter that the beam can be subjected to without producing tensile stresses in concrete. So meaning the resultant stresses given the loading and the pre-stressing force at the bottom fiber, is 0 tensile, no? So okay, so part 1. So first we will calculate the top and bottom stresses at the top and bottom fiber. So this is at the end span due to initial pre-stressing force only. So the formula we'll be using is this one. So this is only due to pre-stressing force. So axial stress due to pre-stressing force P, and bending stress due to axial due to the eccentricity. So yung loading na bending moment due to loading, so hindi pa muna kasali because the question muna is due to initial pre-stress. So this is I for initial. Okay, so now we have the value of P, B, D, and E. So i-input lang natin. So we have 171,750,000 Newton. So MPa is Newton per mm, no? So that is MPa. So dapat units natin is in Newton for forces, and for dimensions or measurements is mm naman. So we have 1,750 kilonewton is 1,750,000 Newton over 300 mm by 600 mm plus minus 6 times P 1,750,000 times 220 na yung eccentricity natin. So input lang natin yung mga values over 300 times 600 squared. So we can solve negative 9.722 plus minus 21.39. Okay, so for the top fiber, we have the plus sign. So plus for the top fiber. So negative 9.722 plus 21.39 is equals to 11.67 MPa. So that is the stress at the top fiber due to initial pre-stress. Now at the bottom naman, so negative. So sa bottom negative. So we have negative 9.722 minus 21.39. So we have negative 31.11 MPa. So sa sign conversion natin, negative is denoted for compression. So of course, since the pre-stressing force is below the neutral axis at an eccentricity, so the bottom fiber should be in compression and the top fiber should be in tension. So these are the values of the stresses at the top and bottom fiber. So that is for the part 1. Okay, so part 2. So sa part 1, na-solve natin yung top and bottom stresses. So sa part 2 naman, we will calculate the stresses at the top and bottom fiber, again in MPa, of the beam at mid-span. Okay, so very important no saan yung kino-consider mo na location. So for loads, so sa loading, yung effect ng load sa beam is maximum sa mid-span. So sa pre-stress naman is sa ends, no? So doon yung pinaka-effect nung forces applied. So due to service loads, so at mid-span due to service loads and pre-stressing force. So this time combination na ng pre-stressing force and yung applied or yung service loads natin. So first is we will calculate yung distributed load natin na omega. So first we have 15 kilonewton na live load. So we have 15 kilonewton per meter. And then 5 kilonewton per meter na superimposed dead load. And for the weight, so yung weight natin is, we have the unit weight of concrete is 23 kilonewton per cubic meter. So we will multiply the cross section of the beam. So that is 0.3 meter by 0.6 meter. So magiging kilonewton per meter na siya. So the total distributed load for the beam is 24.14 kilonewton per meter. Okay, so now we have the dead load. We have the distributed load. So we will solve the maximum moment for the beam, which is at the midspan. And the formula for that is omega L squared over 8. So we have 24.14 for the distributed load times 12 meter na span squared over 8. So the maximum moment at midspan is 434.52 kilonewton meter. So after solving the moment, so we will now use the formula for the bending stress due to load. So yung kabila, so yung sa review natin kanina, there is a three components yung formula. So first is due to pre-stress, which is yung dalawa, axial and bending due to pre-stress. And ngayon naman, this is due to service load. So na-solve na natin yung due to pre-stress, which is these values. No? Ngayon naman yung due to loads or yung service loads natin. So we have minus plus 6 times the moment due to load over BD squared. So we will substitute the value. So 6 times 434.52 times 10 to the power of 6. That is to make it in Newton mm. And then times 300 over 300 times 600 squared. So that is mm squared. So magiging Newton mm na lang siya. So the value is for the stress due to service loads is 24.14 MPa. So that is for service loads, yung effect niya sa beam is equal siya no sa top and sa bottom due to loading. So yun. So we will now combine these stresses. Okay, so first is due to pre-stress with loss na siya. So since we have to consider 15% loss at service load. So meaning pag initial pa lang na pre-stress, wala pang loss. But pag nag-apply ng loads, the pre-stress forces or pre-stress na mga stresses is nagkakaroon siya ng mga losses. So you have research on that. So meron kayong assignment tungkol dyan. So yun yung mga losses na yun. So this is the accumulation na ng mga losses. Okay, so first is sa top fiber. So we have 11.67 due to pre-stress. But since we have a 15% loss, so we will multiply 1 minus 0.15 or directly multiply 0.85 para ma-reduce yung 11.67. So we have positive 9.92, meaning that is in tension. So 9.92 megapascal. So sa bottom naman, we have 31, negative 31.11 minus 15%. So magiging negative 26.44 megapascal na lang yung stresses due to pre-stressing force. So ito yung magiging diagram niya. So we have a tension sa top and bottom sa fiber, compression sa bottom fiber. So now plus due to loading naman, so we have 24.14 megapascal. This one and so ito. So due to loading, so the beam tends to bend downward, no? So meaning at the top fiber merong compression and tension sa bottom fiber. So equal sila. So the resultant force is 9.92 minus 24.14. So that is negative 14.22 megapascal. So this is compression. And sa bottom naman is negative 26.44 plus 24.14. So that is equal to negative 2.30 megapascal. So this is the resultant stress for a pre-stressed force. So dapat yung matitira lang or yung resultant na stresses are compressive or zero compressive or zero tension sa baba. So na-eliminate yung mga tensile stresses. So this is the answer for question number 2. So that is top and bottom stresses at the end fibers. Okay, so number 3. So calculate the maximum additional uniform load that the beam can be subjected to without producing tensile stresses. So since sa resultant stress natin, given the calculated natin na distributed load, medyo in excess siya, no? So malakas pa yung beam natin. So the question here is, without producing tensile stress. So meaning, i-zero natin yung sa bottom fiber. So i-zero stress. So that is, ma-maximize siya. So ma-zero yung tensile stress now. So sa part 3, so we will add, so since this is negative, so we'll add 2.30 megapascal para maging 0 siya. So to balance yung sa bottom. So that para maging zero stress na or zero tensile stress yung sa baba. Okay, so stress is equals to, so yung formula natin, 6m over bd squared. So this value should be less than 2 point, or is less than or equal to 2.30 megapascal. So using this formula, we can solve the moment since we have bd. So moment is equals to 2.30 times 300 times 600 squared over 6. So the additional moment is 41.48 kilonewton meter. So parang pabalik tayo, no? Pabalik yung magiging solution natin dito. So given the stress, kukunin natin yung load. So kanina, given the load, kukunin natin yung stress. Okay, so the moment is equals to omega L squared over 8. So this value should be less than 41.40 kilonewton meter. And ito yung hinahanap natin, yung additional na distributed load. Okay, so 41.48 times 8 over 12 squared. So i-transpose na natin yung mga values para ma-left out yung omega or yung additional distributed load. So the answer is 2.304 kilonewton per meter. So for this type of beam, or for this beam, you can add 2.304 kilonewton per meter na additional distributed load. So kaya pa niya yun. So that is the final answer. Okay, so that is how you solve pre-stress members, considering yung mga loading, yung pre-stressing force, and calculating yung mga stresses. Okay, so next problem. So situation 2. So the pre-stressed hollow core slab. So this time, hindi na siya beam but slab na siya. So I guess you're familiar with hollow core slabs, no? So it is a pre-casted na mga slab. So pre-casted slabs yung hollow core slab natin na yung dimension is meron siyang length dito. So say ganyan. So this is L. So yung hole niya is through and through siya. So this is a hollow part. So yung mga ito is mga hollow part na to. So these are pre-stressed pre-casted na mga slabs. So this is the new applications for the precast na mga structural members. So okay, so the properties of the slab is area. So yung area niya is 1.4 times 10 to the power of 5 millimeter squared. So thickness is 200 mm. The base or the width is 1.2 meters. And section modulus. So section modulus is I over C, no, initial stress, no, moment of inertia over the C, or yung outermost fiber. So 6.8 times 10 to the power of 6 millimeter cube. And live load is 2.8 kPa. Superimposed dead load 2.2 kPa. Slab weight is 2.8 kPa. And pre-stressing force is 830 kilonewton at an eccentricity 64 mm below the neutral axis. So since this is a hollow core slab, yung thickness din niya is usually around 200 mm. So kasing kapal lang din ng mga on-site casted na mga slab. So this slab is simply supported on a span of 8 meters. So Yung span daw niya is 8 meters. So allowable stresses at service loads are, so we have here an allowable stresses, so meaning we should not exceed on these values. So allowable stresses at service loads are 2.8 MPa and tension in tension and 6.8 MPa in compression. So since this is a precasted na slab, so meron na siyang properties, no? So kung ilang force lang yung kaya niya, ilang loading yung kaya niya. So for this case, yung slab natin is meron siyang limit na 2.8 megapascal on tension and 16.5 megapascal on compression. So yan yung strength ng slab natin. So still we are considering a 15% loss of pre-stress at service load. So we are required to calculate the following. So first is the stress in MP at the top and bottom fiber of the slab at the ends due to initial pre-stress. So kagaya din nung example kanina. So stresses again at the top and the bottom fiber at mid-span due to loads na and pre-stress. So combination na ng due to pre-stress and due to loads. And next is the maximum additional load in kilonewton per meter that the slab can be subjected to if the allowable stresses at the service loads are to be exceeded. Okay, so same problem sa previous module, but this time slab yung gagamitin and we have to consider an allowable stresses na. So okay. So first question is the stresses at the top and bottom fiber of the slab at the ends due to the initial pre-stressing force. Okay, so the formula again is ito. So since hindi na siya rectangular na beam, so irregular na yung area natin kasi may mga hollow na siya. So we will use the original formula. So that is P over A plus minus PEC over I. So okay, so since we are given with the section modulus, so we will use section modulus. Okay, so again, section modulus is equals to I over C. So that's why ito is magiging S na lang siya. Okay, so now we will enter the values. So 830,000 Newton over 1.4 times 10 to the power of 5. That is the area. And then plus minus 830,000 times 64 over 6.8 times 10 to the power of 6. So the value of the stress due to initial pre-stress is negative 5.929 plus minus 7.812 megapascal. So at the top of fiber, so plus sign yung gagamitin natin. So the answer is 1.883 megapascal. And sa bottom naman is negative yung gagamitin natin. So that is negative 13.74 megapascal. So these are the stresses at the top and the bottom fiber of this slab due to initial pre-stress. So initial pre-stress pa lang siya. So this is the first part. Now for the second part, the stress in MPa at the top and bottom fiber of the slab at the mid-span due to loads and pre-stress force. So ngayon naman, i-calculate natin yung due to loads and then yung combination ng loads and pre-stress. So we have solved that at the top and bottom fiber. These are the stresses present. So again, we will solve the distributed load. So distributed load due to dead load, live load, and superimposed dead load. So i-add lang natin, no? So 2.2 kPa due to dead load, 2.8 due to weight, and 2.8 due to live load. So multiply natin ng since kPa is Newton per mm squared. So, i-multiply natin ng Newton per meter squared yung kPa. So, i-multiply natin ng 1.2 meter para maging kilonewton meter yung yung unit natin. So, unit ng distributed load is Newton per meter or kilonewton per meter. Okay, so this is the 1.2 is yung base natin or yung width ng slab. So, yung width ng slab is 1.2. So, the value or the total distributed load that the slab will carry is 9.36 kilonewton per meter. Okay, so again, we'll be solving the same procedure. So the maximum moment at the mid-span is omega L squared over 8. So 9.36 times 8 squared over 8 is 74.88 kilonewton meter. So that is the maximum moment at mid-span. So the stress due to bending, due to the loading, so this is negative minus plus m over s. So this is originally mc over I. So but section modules binigay sa atin. So this will be m over s. So is equals to 74.88 times 10 to the power of 6 to make it Newton mm, and then 6.8 times 10 to the power of 6. So mm na siya. So magiging 11.01 megapascal minus plus. So yan yung stress natin due to the loading natin, yung distributed load. Okay, so now we will combine the stresses. So we have solved the stresses due to pre-stress and stress due to loading. So due to pre-stress, so we have a 15% loss. So we will subtract 15%. So magiging 1.601 na lang yung 1.883. That is the stress at the top fiber. So sa bottom fiber naman, so we have negative 13.74 minus 15% is negative 11.68. So this will be the stress diagram. And then due to loading na naman, so we have 11.01 megapascal. So this is the negative sa top and positive sa bottom. So the resultant stress is negative 9.41. So that is 1.601 minus 11.01. So that is negative 9.41 megapascal or compressive stress. And then 0.67 megapascal at the bottom. So ito yung stress diagram natin. So all compressive. Okay, so these are the values for the top and bottom fiber stresses due to loads and pre-stress. Okay, so the third question is, what is the maximum additional load that the slab can be subjected to if the allowable stresses at service loads are to be exceeded? So, meaning, yung limit niya is yung allowable stress na binigay sa atin. So that is 2.8 megapascal and 16 megapascal for tension and compression respectively. Okay, so na-solve na natin yung stress due to given loading. So that this is the total stress due to pre-stress and the loading. Ngayon naman, we will try to add yung additional loading. So the stress due to additional loading. So additional stress sa compression and additional stress sa tension na sides. So this combination, so yung pag i-add mo yung additional stress natin, the value should be less than the given allowable stresses, which is 16.5 megapascal at the compression side and 2.8 megapascal at the tension side. Okay. So first is ito yun. So, i-add natin, no? So, negative 9.41 plus the pre-stress additional stress due to the stress due to additional stresses. So, hindi mo natin nilagay yung sign since this is considered as compression na. So, we have denoted it as compression na. So, the value of the additional stress should be less than 7.09 megapascal. So that is considering yung allowable stress natin at the compression side. So at um, the tension side naman, so we have um, negative 0.67 plus the additional stress due to the additional load should be less than 2.8 megapascal. So this will be 3.47 megapascal. So among the two, kukunin natin yung pinaka maliit, no? So, kasi kung malaking kukunin natin, mag-exceed siya ng 2.8. So, sa 3.47, mamimit niya yung dalawang allowable stress. So, pasok siya sa allowable stress natin. Okay, so we will use 3.47 megapascal. So, again, yung formula, stress is equals to moment over section modulus. So, the additional moment should be less than 3.47. So, multiply natin yung section modulus, 6.8 times 10 to the power of 6. So, magiging 23.596 kilonewton meter yung additional moment. Now, to find the additional distributed load, moment is equals to omega L squared over 8. So, leaving out omega, so magiging 8 times 23.596 over 8 squared. So, the value of the additional load is 2.95 kilonewton per meter. So, yan yung additional distributed load, maximum additional distributed load na pwede natin i-add or i-subject dun sa hollow core slab natin. Okay. So, that's it for the stresses calculation. So, you can practice solving problems online. So, sa YouTube, maraming available na mga videos. So, this ends our module 3. So, thank you for listening and have a good day.